Just to give you a little bit of information about Nylacast, we supply plastics and parts all over in 43 different countries. We have 350 employees. We work in a multitude of market segments, which gives us a lot of expertise in different areas, which helps us translate those experiences to other customers' applications. So if they come with us with something unique, we're able to possibly find something similar to an application issue that we've dealt with in another market segment, and then hopefully help new customers with those. We do a lot of investment inward in our manufacturing process. These are the quality standards that we currently manufacture to and are certified to. We have a full in-house research and development testing facility, fully independent, run by our own people. We can do any kind of tests for our own internal needs, as well as specific information that customers may be looking for, help them with identifying materials, or in general, any kind of laboratory work that you guys may need. We can do it all in-house, internally. We also have a dedicated engineering team where we can do design, analysis, FEA work. We can also help with any kind of project management, because we're experts at it because of the quality standards that we already manufacture to. And we can also help with any R&D projects that you guys may have. And I've got quite a bit of material to go through, so I'm going to speed through these initial slides because I want to make sure I hit as much of this as I can and don't run out of time. And I only have 30 minutes, so I'm going to really be hitting this at a pretty high level, just kind of giving you guys an overview of my thoughts on how the best way it is to start thinking about how do you pick a plastic for your application. And when you look at engineering materials, typically they fall into these categories that engineers work with: metals, ceramics, polymers. Polymers is becoming a big part of engineering substrates that engineers are being able to utilize because of some of the unique characteristics that they bring to applications, and I want to kind of go over that a little bit with you. What I want to kind of give engineers is some perspective about where plastics fit. And when you look at the weight of a plastic, density, I've taken nylon, which is what we consider to be a commodity material in the marketplace, polyamide imide, which is a high performance plastic, and then compared it to a couple of metals: bronze, steel, aluminum. So when you look at the density of materials, you can see right away plastics bring considerable weight savings in an application. Even against aluminum, we're still half the weight of aluminum. Tensile strength, this is where we start really separating the materials. As you can see, plastics are not as strong as metal. Modulus of elasticity, we're nowhere near as stiff. Now we can change that with different additives. We can put fibers in it: glass fibers, aramid fibers, carbon fibers, but still metals, that's where what their advantages are. But when you look at the relative strength to weight ratios, plastics provide a lot of value from that perspective. Another big challenge design engineers have to deal with is coefficient of thermal expansion. Plastics grow and expand a lot more than metals do, and it's something that you have to take into consideration in your designs. And I'll cover that a little bit in the slides. I'll get this right. There we go. Just some of the benefits of thinking about now. What Nylacast does, we manufacture plastics in either a rod, a sheet, a tube, and then sometimes they're available in films that engineers can take and manufacture one part or 5,000 parts, however many parts you want. So I'm not going to really be talking about injection molding in general, although you can use some of the things I'm going to give you for injection molded parts, but we're primarily talking about parts that are going to be machined from some sort of stock shape. And the value in general plastics bring, especially lubricated or bearing and wear plastics that are going to be used in tribological applications. Plastics generally don't wear the mated surface, so it's typically the sacrificial material. So if you have a bearing grade bronze or brass wearing against another metal, typically both of those parts are going to wear. With plastics, it's usually the plastics are going to wear. Now there are some exceptions to that, but in general, plastics generally have very good chemical and corrosion resistance, reduce weight. We can also lubricate these materials internally with different kinds of oils, waxes, Teflons, also molybdenum disulfide to enhance the lubrication. So if you have supplemental lubrication systems or you need to get rid of lubrication, contamination maybe, these materials can work without lubrication in your application. We also are good at dampening sound, electrical insulation, thermal insulation. The materials are typically colored all the way throughout, so if you need to use colors to delineate parts or show different things in your design, you can use colors to differentiate a lot easier with molded materials. They're also a lot easier to fabricate and machine than some metals that are out there, and we can mold different shapes and sizes much easier. And then also, if you're looking at prototyping and designing, it makes it much easier to start to change your designs, because you're not building a tool for an injection molded tool and then having to, if you do need to make a change, then build a brand new tool for a brand new part. You can easily change parts by machining it. So if you look at the way the typical plastics industry presents the products, you're going to see it usually represented within a triangle. There's going to be a triangle, and it represents, they populate it with different materials. So thinking about that triangle, I'm going to use sort of a goofy analogy here. And for this conversation, I'm primarily going to be talking about two different materials. There's 3 or 4 groups of plastics, but I'm just going to focus on the 2 primary ones right now. So on the left side of the triangle, you're typically going to see plastics that are workhorses, like a van. On the right side of the triangle, you're going to see materials that are kind of higher performance. So let's think of them like a sports car, so to speak. As within a van or a sports car, if you get a base model versus a model with higher options on it, the higher the performance, the higher the cost. So you're going to see the same thing in the representation of a triangle for the plastics. The further up the chart or the triangle we go, the higher the performance typically, and the higher the cost of the material. So take away that goofy analogy, and let's start plugging in what I mean by that. The left side of the chart are going to be plastics that are amorphous. The right side of the chart are plastics that are semi-crystalline. I'm not going to get too deep in the weeds on it, but it's important to know that as far as your material selection, because knowing what amorphous versus semi-crystalline mean kind of help you understand and start categorizing plastics. So when you're thinking about how do I pick a plastic for the application, the way I look at it, it's like you're trying to segregate these materials down. There's a commercial in America of a car company selling used cars, and they have a guy standing in a large room, and he's like, I want to buy a white car. And then so all these white cars come rushing by. I want a white car, but I want a convertible. And then now they're all white convertibles. And that's kind of the way I start thinking about these materials. So once you start thinking about your application and what you're trying to do, you can start segregating these materials down to fewer and fewer materials, so that you're limiting your research to just a few materials instead of this big basket of products that are out there that can kind of be overwhelming when you're trying to decide. So amorphous is referencing the molecular structure of the plastic. The molecules tend to be sort of randomly oriented. Semi-crystalline, there's going to be some orientation, some alignment, some orderliness there. And what that means is, knowing that, is that the amorphous plastics tend to be transparent. Those are plastics like polycarbonate, acrylics, Ultim, and there's a couple of other materials, polystyrenes, PETGs. These plastics tend to have pretty good dimensional stability, very good ductility, pretty good resistance to acids and bases, and they're thermoformable. When you're making prototypes, that means you can heat these plastics up, drape them over a mold or a tool, and then make parts very quickly and easily. On the semi-crystalline side of the chart, these plastics tend to be opaque. They have very good tribological properties typically, not all the way across the chart, but some to varying degrees. Very good creep characteristics, very good fatigue resistance. Also, they tend to be very resistant to multiple chemicals as well as hydrocarbons. These plastics generally are not thermoformable. So take all of that out. Now I've taken the triangle and I've populated it, and you're going to see typically the material broken out by temperature range. So as we go up the chart, we're getting higher temperature range plastics, and then they're separated out whether they're amorphous or semi-crystalline. And this is important because let's say you know that you're going to be working on a bearing. Well, you're automatically going to be able to segregate out the amorphous plastics, because amorphous plastics generally don't have good bearing and wear characteristics. So you've effectively eliminated 50% of the plastics that are out there for your bearing application, because you're just thinking about, well, that's what I need, and then we can get rid of those. And then we start separating them out even further by temperature, by some other aspects, and I'll go through that in just a second. Trying to almost getting ahead of myself. Okay. One of the things I want to stress is that engineers tend to put a lot of emphasis on printed data. You need to be careful with plastics, because property data is not very specific. We can take a nylon 6 like Nylacast manufacturers, and you can take nylon and you can look at the properties for cast nylon, extruded nylon, molded nylon, injection molded nylon, and they're all very different. So you just can't take one and say that's the properties for nylon, because the way the product is manufactured plays a big role in what the properties are ultimately for that part. So I would say use the data to be able to get to where you need to be, and then test to prove it. All right, when you're looking at material selection, it tends to fall into this sort of process. You know, what are the physical requirements? What's the environment that those polymers are going to be used in? You know, as in the physical performance side, is it going to be a bearing and wear? Is it going to be a static or a structural application? What kind of dimensional stability do I need? What kind of strength and stiffness? Environmental, what are the thermal aspects? What kind of temperatures is the plastic going to see? What kind of chemicals are going to be involved? And then we get into other. It's like, I have to have it pink, or it needs to be has to be able to be used with food contacting applications. You know, part geometry plays a big role in the application, and then also manufacturing processes. You know, is there a manufacturing process that can produce the part that you need? It may not be out there in the plastic that you want. So when you look at the application process, I like to break it into these 5 areas. Number one, what's the temperature range that we're working in? That's very, very important. And we'll be glad to share this presentation with anybody if you guys would like copies. Now, this is different than what I'm going to give you, because I made it a little different so that I can present it a little easier. But number one, what's your temperature range that you're working in? What are the mechanical loads and stresses that the part's going to see? If it's a bearing and wear application, what kind of bearing is it? Is it rotating? Is it sliding? Are there any abrasives in that environment? What kind of abrasives? Because that makes a big difference. Some plastics are good with some abrasives, some aren't good with others. What are the chemicals that the plastics are going to see? That's incredibly important right there. Are there any electrical considerations? Do it need to be an insulator? Am I concerned about static? Do I need static dissipative properties? And then what are the other? Color, food compliance, etc. Okay. So the first part of it is, what am I going to do with the part? Is it going to be bearing and wear, or is it going to be structural? And then we start breaking it down from there. What I tend to do is look at the materials by their grouping: semicrystalline, amorphous, and I've added imidized in here, and then there's also another set called thermoset. And then you can look at those properties and know, well, these generally have these kind of properties, and then so what are the plastics underneath that group of properties that tend to fit what I need for my application? So these are the plastics on the left side, far left side: ABS, acrylic, Kydexes. These materials are all amorphous, and they have those characteristics, the same for semicrystalline and the same for imidized. All right, so again, we're still trying to break it down. We're slowly saying, okay, these are the things I need, and narrowing the focus further and further down. So when you look at, if it's a structural application, both amorphous and semicrystalline, thermoset, the world's your oyster virtually in a structural application, because anything will pretty much work. We can adjust the properties. Let's say if you look at a plastic and you need something stronger or stiffer, there are additives that are out there that can improve different aspects of the polymer. We can use different kind of fibers, all different lengths of fibers, etc. And those fibers generally work on improving modulus, but most of the time we lose toughness. It tends to be a little bit more brittle sometimes, depending on how much additive and what we put in there. It also allows for higher temperature and higher loads in your application, depending on which fiber that we're looking at. A lot of the fillers improve wear. Glass, molybdenum disulfide, PTFEs, for example, can improve wear significantly in your in that application. And then, of course, colorants change the appearance. Just to give you an example of the ways engineers can think about it. Now, these are different kinds of plastics that are out there available right now off of the shelf. These are the Nylacast products. You can see we make a base nylon, and then we have a molybdenum disulfide filled nylon. We have oil filled nylon. We have oil and lubricant filled nylons. We have glass filled nylons. We have heat stabilized nylons. So there's a lot, and I'm not going to get into the details of each, but as you can see, these are all different additives that are there to enhance the property values that could slightly improve that plastic to be a better fit for your application. These are just examples of some of the standard formulas that are out there for compression molded or extruded applications, where just say you're interested in PEEK and you're like, I really like PEEK, but I wish it had a little bit higher modulus. Then there's possibly a glass filled version out there, a carbon fiber filled version that could get the modulus where you need it. And again, these aren't exotic materials. These are readily available in the open market in small volumes. And we go up the chart to polyimides and polyamide. I'm just trying to show you that, let's say there's a PEEK up here with a 10% PTFE, which helps with the lubrication, makes it a much better bearing, lower coefficient of friction, but we need a little bit higher strength and stiffness, so it's got some carbon fiber mixed in with it, and also some graphite mixed into this one too. So you're really limited by your imagination as to what you can do to these polymers with today's technology to enhance them and change them to be a better fit for your design. If you're thinking about a bearing and wear application, again, the semi-crystalline materials are the materials that you need to focus on, and the imidized materials at the top of the chart. The wear and dimensional stability of those materials are also enhanced by all these different additives that we just talked about. And a lot of these plastics, there's data available for PV, pressure times velocity, which is a great way to help you segregate out which plastic is a better fit for your application based on its PV performance. So that's a good way to help you pick a material too if it's bearing and wear. Okay, the next aspect I like to focus on after you've decided what I'm going to make is what's the temperature range. Temperature is a very important aspect of choosing a plastic for your application. A lot of marketing data that's out there gives you a continuous use temperature. In my opinion, it's not very valuable. It's sort of a piece of information that the resin people come up with that basically say this is where we think this material can operate. But I challenge that, and I'll show you why in just a second. I would, as an engineer, I would spend my time looking at the heat deflection temperature. Again, I'm giving you standards from the U.S., so I don't have it in the European, what the European ISO standard is, but looking at the ASTM standard for heat deflection temperature, and I know the ISO standard's very similar to it. The data is given to us in two pressures, 66 psi and 264. What's important about this is the temperature at which that plastic is starting to change, and so you're going to be given that data under load and with minimal load, which is very important to know in your application as to what's going to happen to that plastic at my operating temperature. And the reason it's important is temperature affects strength of the plastic significantly. This is a dynamic modulus chart, and what this chart is, they plotted the flexural modulus in relationship to the temperature. And I've got a lot of different plastics here, and I'm going to pick on PEEK, polyether ether ketone, which is Godzilla of the thermoplastics. It has the highest properties of thermoplastic. But if you look at the property data, it quotes 480 to 500 degrees continuous use temperature. And it's true, at 500 degrees Fahrenheit, PEEK is still in existence. But if you look at its heat deflection temperature, which is this dark green, right here is the heat deflection temperature. That's the temperature at which the plastic starts to soften. It's often referred to its knee. So this is important. So if you're operating at 450 degrees and you choose peak based on the continuous use temperature, sure, it's working at that temperature, but it's the delta between its modulus at room temperature, or the data sheet that you use, versus your actual application. It's lost 50% possibly, depending on what's going on in the application, of its modulus, which could be significant in your application. And then this is also a good illustration of how fibers affect the polymer. Let's take PEEK, still using it. Here's unfilled PEEK, PEEK with glass, PEEK with carbon fiber. You can see it pushes the modulus up significantly, but the knee is still there. It's still, heat deflection temperature is still in that range. It pushes it off slightly, but it gives us a higher pressure to operate in your application, which means that that fiber additive could help PEEK work in your application. And you can see with carbon fiber, it gives us even higher modulus. Also, how long is the plastic going to see the temperature? Is it long term? Is it intermittent? You could find a plastic that could work if it's only going to see that high temperature for a very short period of time. Again, what are the loads and stresses? Tensile strength is important. There's a lot of data out there where we have the data for the tensile strength to help you, and it's apple to apples. Typically, it's given in ASTM or the ISO standards so that you can help break it out. If you have an idea of what kind of stress that you're going to be exerting on the plastic, how to break it out and segregate out which plastic's the right one. Same thing for Flexural modulus. We have all this data. I'm just going to spin through these because I want to make sure I get through everything. Elastic behavior is another thing that engineers need to take into consideration. Plastics are going to move. I don't care what you put in it, it's going to move. The yield stress is lower, the strain is definitely much higher. So you need to take that into consideration. The effects of time, temperature, and load on that part is going to cause it to change, and it will move. It's just a matter of how much based on what we put in it. And I'll talk a little bit about creep later, but what are the wear properties? There's a lot of data out there that can help you guys segregate out the materials based on how well this material is going to work in your specific application. Again, there's a lot of research being done with different kinds of abrasives that can help you guys narrow the focus down again and get you closer to what kind of material that you need for your application. What kind of abrasives is important too. Some plastics are good at sand, some are good at coarse sand, some are not so good with fine sand. It really depends. There are generally, though, polymers that have good abrasion characteristics. The typical test is a sand slurry test. They take a circular coupon of various plastics, same thickness, same diameter, put it down in a sand slurry, and just spin it for X number of minutes at an X speed, and then they weigh it before and weigh it after, and that gives you an idea of how much material loss. You can see UHMWs and nylons tend to have much better wear performance. Those are plastics that are in the amorphous or semi-crystalline side of the chart. Electrical insulation. I had someone earlier ask me about the volume resistivity of a plastic. They were concerned about conductivity, and we have a lot of information about the plastics that are out there, what their volume resistivity and dielectric properties to help you if you need conductive characteristics. Say you're going to be making a product that's in a volatile environment and you're concerned about static and arcing. These materials already have some degree of conductivity depending on the additive, but there is a lot of technology out there right now with nanotubes and other kinds of additives to give you very specific conductivity for your applications if you're looking for static dissipation and or insulative properties as well. Chemicals is very important to think about. This is a really hard one. And there's a lot of information out there about which plastic is, how plastics react to various chemicals. I would suggest you do a ton of research. Ask every chemical possibly that could come in contact. Even chemicals that are used while they're machining it have an effect on the plastic, possibly long-term down the road. If they're using a solvent as a coolant, et cetera, et cetera. I have in my office a volume of 6 books covering chemical resistance in polymers, and it nowhere near covers all the different plastics that are out there and all the different concentrations and all the different chemicals it could be. This is very, very important. Pay very close attention to the chemicals that are involved in the application. Water especially, some plastics absorb a lot of water, and some chemicals can attack plastics significantly and melt them in your environment or cause the plastic to craze and crack further down the line. Generally, if you're concerned with chemicals, I would be looking more on the semi-crystalline group. These plastics have very good chemical resistance, some to greater degree than others, but that group of plastics includes plastics like Halar and polytetrafluoroethylene, Teflons and so forth, Kynars, which are very chemical resistant plastic if you're not familiar with those. Another thing to think about is the impact strength and toughness of a plastic. The notched Izod impact test is a very good test. It gives you a good indication of how brittle the plastic is so that you can compare these other materials as you segregate them down. Let's say you know the application is going to see a lot of impact or a lot of stress. You want to be looking at plastics that have a higher impact strength and that it's not so brittle. And this is a way to help segregate it out by how tough it is. Dimensional stability is very, very critical in bearings and bushings especially, but a plastic under load will move. Unless, depending on how you've got it captured, you're going to have creep issues long-term in your application. So I would absolutely be considering that if you're concerned with dimensional stability, long-term dimensional stability in your application. Again, there's a lot of information on that. The next big problem is coefficient of lineal thermal expansion. A plastic like UHMW has very high coefficient of thermal expansion. We just took and did a simple run through the numbers here. This plastic only changed degrees from room temperature 47 degrees higher and will grow up to 1/2 of an inch. So that could be a big problem in your design. Now, I'm not saying that eliminates it from this, but it means we need to design to allow for that thermal expansion, which we deal with all the time with this particular plastic and can help. Water absorption, I've already touched on it. I would pay very close attention to water absorption. I'm going to move on because I'm running out of time. Part geometry is critical. The number one failure I typically see falls into this range right here. Whenever I see designs with sharp inside corners, this is where you're going to have problems typically. It depends on the plastic. UHMW, it's not so much of an issue, but on other polymers, this is critical. I tend to recommend these kind of radiuses if possible, and eliminate threads in any plastic design if you can. I recommend inserts, and I have some examples of how we do it just to show you if you guys are interested. This is an example. I told a customer to use an insert. They used a threaded insert, and it cracked. What complicated this, and this is something engineers, you need to get out on the floor and check and see how the assemblers that are assembling your design, if they're using any kind of thread lockers. I do not recommend thread lockers on plastics, even the ones that say that they're for plastic. This was a Loctite thread locker for plastics, and the part stressed and crazed and cracked. And it was complicated by the sharp thread roots of that design. And if there's anybody from Loctite in here, don't throw anything at me. Look at your part, the way that you're assembling the part. Avoid countersink at all possible in your design, if at all possible. It forms driving that angled screw into the product forms stress around, hoop stress around it. You're definitely going to see creep and cracking and stress crazing around that part. I recommend a complete through hole or a counter bore. UV exposure, make sure you're looking at that. Is the part indoors, outdoors? Make sure it's formulated to handle the UV light, because UV light will definitely degrade the material. Also sterilization, if you're making medical devices or so forth, there's a lot of information out there. This is critical. Some plastics are good at being sterilized, some are not so good, which could also help you in your design. If you're needing, if you have a medical application or an application that's going to be autoclaved or sterilized, maybe a less expensive material could be used because it's only going to be used in a couple of times and then disposed. Regulatory compliance, there's a lot of information out there. Again, this is all American-based data, but here is a spreadsheet if it comes up. Let me just open it. Did it come up? There it is. This is a spreadsheet. You can get the ASTM data by resin for whatever it is, what kind of regulatory compliance information that you need. How do I get rid of that now? Do I just go click back on the screen? There it goes. Okay, good. Also, again, these are the FDA. Let's say you know your plastic's going to be used in a food contacting application. There's already groups of plastics specific for food contacting that are out there that can help you, again, segregate the materials down so that you're minimizing the number of materials that you're having to research. Color, not all plastics are available in every color. Let's say if it's a bearing application and it has molybdenum disulfide, that part's going to be black. You can't make it pink. You can't make it red. It's going to be black. So it depends on the additive. So think about that long term in your application. What kind of colors? Machining characteristics. There are some perfect plastics for your application that your machinist will shoot you for choosing because they're horrible to machine, or they're difficult to machine, or they're hard to hold tolerances in. So think about that in your design. How does this material machine? And these are all questions that your suppliers can answer for you. Other characteristics, the color I just mentioned, the size. Some plastics, let's say I needed an 8-foot diameter ring. Well, you're not going to be able to get PEEK in an 8-foot diameter ring. You could get nylon in an 8-foot diameter ring. So size plays a critical role. Sometimes these plastics can't be made the way you need it. Already talked about machining. Just to make it easier for you, at Nylacast we have a worksheet where I cover the 5 areas: thermal, electrical, chemical, mechanical, other, and I ask some basic questions. If you have an application and you're curious maybe what materials I'm thinking for your application, I'd be glad to help you. Just fill in the blanks for me. I'll kick you back an email with a group of materials that I think would be a good fit for your design. And with that, I'm out. We're at booth E70, so if you have any detailed questions or any other application questions you want to talk about, I'd be glad to help.
Thank you very much, Jody. Fascinating presentation. Thanks very much. Cheers.